Thank you for the introduction. And also, I'd like to start by thanking the organizers for the invitation to IHS. It's my first time here. And also for this opportunity to give a talk at this wonderful conference. So the subject of my talk would be global regularity and scattering properties of two nonlinear wave equations, which you can think of as generalization of the Maxwell equation. So we'll start from there. So Maxwell equation is a system of linear equations which concern a real-valued one form on a space-time, which is supposed to be the electromagnetic potential. And in my talk, my space-time will always be the Minkowski space, the plus one-dimensional Minkowski space. And from this, you define what's called the electromagnetic field, which is nothing but the curl of A. So this is the antisymmetric part of the gradient of A. And the Maxwell equation reads as follows. It's the space-time divergence of the electromagnetic field is equal to the charge current vector. So this is the inhomogeneous term for the Maxwell equation. The first nonlinear equation that will be the subject of my talk is what's called the Maxwell-Klein-Gordon equation. Which is a nonlinear generalization of the Maxwell equation by coupling it to a scalar field which evolves via a Klein-Gordon equation. So how this looks is as follows. So this is an equation for an electromagnetic field, potential, and a complex valued scalar field, which I call phi. So the electromagnetic potential acts on phi as a potential in the Klein-Gordon equation. Okay, so in order to make sense of that, I introduce what's called the covariant derivative, which is a first-order operator, which is in the mu direction. It's just the partial derivative plus the potential term given by the electromagnetic potential. Okay, and then the phi equation, the phi satisfies the Klein-Gordon equation. But with respect to this covariant derivative, and then the A evolves by the Maxwell equation, where the source is given in terms of phi by the following expression. So it's the imaginary part of phi times the complex conjugate of the covariant derivative of phi. So the second nonlinear wave equation that would be a subject of my talk is the Yang-Mills equation. Which can be also thought of as a nonlinear generalization of the Maxwell equation, but it's a generalization of sort of geometric nature. Okay, so actually, in order to properly formulate this, I want to come back to Maxwell equation and Maxwell-Klein-Gordon equation, and give you point out a important property of these, which is called the gauge invariance. Okay, because that's so I want to get to here. Talk about that first before I want to talk about Yang-Mills. So in both of these equations, there's inherent ambiguity in the description of the solution. Okay, so in the case of Maxwell equation, it's clear by what I mean. What I mean is, if you look at this f, then this value of f doesn't depend on is independent of does not change under the change if you change a by adding a gradient of some real valued function, right? Just because the curl kills the gradient, right? So this is this ambiguity is what's called the gauge invariance of the system, and the Maxwell-Klein-Gordon has a similar invariance. Where A transforms in the same way, and phi transforms by multiplication by e to the I chi. But then once you write like this, you realize that actually this phenomenon of gauge invariance lends a different interpretation of these equations, right? So what you can think is, in fact, the Maxwell-Klein-Gordon equation, the complex field here, can be thought of as a section of a complex line bundle, okay, where which can be identified with a complex valued function by choosing a frame. So by frame, I just mean a choice of basis of the fiber at each point. In this case, it would just be the choice of which vector should be deemed as 1 in the complex plane, right? And then this gauge invariance is nothing but the rotation of the frame at each point. And this derivative is nothing but the covariant derivative on sections of a complex line bundle. The reason why I set this all up is because Yang-Mills equation is a generalization of the Maxwell equation in the case when the vector bundle has a gauge group which is more general than just the group given by multiplication of this. Okay, so in fact, this can be formulated in a more general way, but let me stick to the most concrete yet non-trivial case. Okay, which is when the gauge group is the group SU2. So in this case, the Yang-Mills equation will be an equation for a one form, which takes values not in the real numbers, but in the matrix algebra little SU2, which is the set of traceless, anti-Hermitian, 2x2 complex matrices. Okay, and then you can formulate a similar connection. So this gives you a connection on vector bundles with SU2 as the gauge group. And then it turns out that the analog of this electromagnetic field is nothing but the curvature to form, okay, which is the commutator of the two covariant derivatives. And you can explicitly compute how it looks like. It looks like the following: d mu a nu minus d mu a mu. So far it's the same as the Maxwell case, but then you have an extra term, the matrix commutator between a mu and a nu. Okay, so you see that the formula from A to F is now nonlinear, and the nonlinearity is due to the non-commutativity of the matrix algebra. And the Yang-Mills equation now reads is the analog of the Maxwell equation with zero source, which is just this. So it's the covariant derivative of covariant space-time divergence of F is equal to 0, whereby this it acts on, you view F as a section of a tensor of which takes value in SU2. So in fact, this what I mean by this is it's okay. And in this case, the there is the same. There is a gauge invariance as well, which is given as follows. So if you take a mu and transform it by the following function. So take any function from the space-time, which takes value in now the group large SU2. And if you make the change like this, then the equation remains invariant. And the interpretation is, of course, that these are the same objects, but just the frames are rotated by this view. So we'll be concerned about large data theory for initial value problem for these equations. And of course, the starting point is the conserved quantities for this equation. So both equations have conserved energy. So in the case of Maxwell-Klein-Gordon, the energy measured at time t of a solution which consists of A and phi has the form spatial integral over the slice constant t of basically the square of the sum of squares of each component of f. Yes?
Maybe this is a silly question. What is the physical significance of SU of 2?
So I just chose it so that it's the simplest example of a non-abelian group. So that it should be the simplest non-trivial example of the equation. So of course you can formulate the equation for other Lie groups, but for concreteness I'll just fix it to be SU2. Any other questions? All right. So the conserved energy for the Maxwell-Klein-Gordon equation is basically just the L2 norm of F and the covariant derivatives of phi. And the conserved norm energy for Yang-Mills equation is basically just the L2 norm of F. So I can write it in this case as just something like this, because now these are matrix valued. And both systems also have okay. So okay. So at least in the massless case here, and always in the Yang-Mills case, you have scaling invariance, and the both systems are, so the systems are invariant under the following scaling. So in the Maxwell-Klein-Gordon case, with mass equal to 0, it's invariant in the scaling where you map A and phi into something like this. So in other words, both A and phi scale like inverse of length, okay, which is natural because A is at the level of a connection coefficient. And in the Yang-Mills case, it's also A also scales like has a dimension of inverse length. And you can see how the conserved energy behave under the scaling invariance of the system, and you realize that for both equations, the critical energy critical dimension is when d is equal to 4. So when the space dimension is equal to 4. So this will be the case that will be concentrated in the rest of the talk. And also I should say that in fact our real motivation will be to try to understand the Yang-Mills equation, okay? But then and Maxwell-Klein-Gordon equation has been traditionally sort of as you will see, shares a lot of analogy with the Yang-Mills equation. Okay, so the viewpoint we'll take is that the Maxwell-Klein-Gordon equation would be a model problem, simpler model problem for the Yang-Mills equation. And in that sense, because the Yang-Mills equation is massless, there's no mass in the Yang-Mills equation, I'll take the mass parameter in the Klein-Gordon to be 0. Okay, so if more properly speaking, one should call this the Maxwell scalar field equation. But fortunately, in the literature, even the massless case is called the Maxwell-Klein-Gordon equation. I'll just stick to the convention. Is it okay? All right, so I'll erase the this here. Then now I'm not lying about anything here. Okay, so in the so dimensions below 4 are so-called energy subcritical dimensions, and in those cases there were results about global regularity of these equations from early on in the 80s and the 90s by the work of early Moncrief and Kleiner, Macedon, and so on. But the understanding of the critical dimension and at the energy regularity has been obtained even in the perturbative regime very recently. So in the case of Maxwell-Klein-Gordon equation, this is a theorem due to Krieger, Disturbance, and Tataru in 2012, that small data global existence hold at energy regularity in d equals 4. Okay, so let me just say the initial value problem for the Maxwell-Planck-Gordon equation with 0 mass. Okay, on R1 plus 4, under some additional gauge condition, I'll get back to this soon. Is globally opposed and scattering holds. If the energy of data is sufficiently small. Okay, and I added this this condition. So actually, so this condition is important to have in order to actually have even a formally well-proposed system. So this is a, and this has to do with the gauge invariance that I explained to earlier here. So by the presence of gauge invariance, if you just write down the equations, then you realize that it's an underdetermined. You have too few equations to have a well-posed system. So you have to. The way you fix it is you impose one more condition that you want your connection to satisfy, and this is one way of doing it, and this is called the Coulomb gauge condition. And the choice here is crucial because it's in the Coulomb gauge where the fine law structure of the Maxwell-Planck-Gordon equation is apparent. This is a observation that goes back to Klein and Macedon in the 90s. There's a corresponding theorem for Yang-Mills equation, and this was proven only last year. Let me just say, same result hold for Yang-Mills. So with this small data result in hand, our goal would be is to address the large data problem for these equations.
What does the schedule mean?
Okay, that's a good question. So it will be a whole story. So let me not get into too much details. But scattering here would just mean that under this gauge, the solution to the problem would converge asymptotically to a simpler equation of But the linear system would be actually not exactly the linear wave equation, but I'll get back. Let me not say too much about this. Okay, so So the question for large data, the large data question for the Maxwell-Planck-Gordon equation is a subject of a result that approved with Daniel Totaro, in collaboration with Daniel Totaro in last year. And we can show that the result is that the global regularity and scattering, whatever that means, hold for arbitrarily finite energy data. So for the initial problem for Gordon in for arbitrarily finite energy So one goal of today's talk would be try to give you a overview of the proof of this theorem. Okay, I should remark that basically at the same time and independently, there was a alternative proof of this theorem by Krieger and Luhrmann. Who followed the Koenig-Merle concentration compactness and rigidity approach to prove this theorem. Okay, and more precisely, they followed the refinement, the development of the scheme due to Krieger and Schlag. Which were done earlier in the wave map case. But as you'll see in this talk, the approach that we take is different. And on the one hand, as you'll see, it is a bit more direct. And on the other hand, the proof that we use relies more on the nonlinear structure of the particular nonlinear structure of the Maxwell-Klein-Gordon equation, I guess, than the other proof. But okay, so this is the picture for Maxwell-Klein-Gordon equation, and then you might ask, what would be the corresponding result for the Yang-Mills equation? And of course, in the Yang-Mills equation, you cannot hope for such a unconditional global oppositeness result because there are time-independent solutions to the Yang-Mills equation which have finite energy, and therefore it doesn't scatter. Okay, so for Yang-Mills equations, these are nothing but instantons, which are solution to the elliptic four-dimensional Yang-Mills equation, which have been studied in the 80s in the geometric analysis community, and moreover. It's also known that instantons can serve as a profile for finite time blow up. So there are explicit constructions of finite blow up known due to Raphael and Luniansky in this case. So in this case, the proper problem, the large data result would not be an unconditional result, but rather the question, until which energy does global oppositeness and scattering hold? So this would be the problem for Yang-Mills equation. And the problem will be as follows: is the energy value problem for Yang-Mills globally opposed, and you have scattering. For energy up to some threshold, and the natural threshold, as I'll try to explain, to conjecture would be that of the first, the ground state, by which I mean the lowest energy, non-trivial solution, time-independent solution to Yang-Mills equation. So the goal of my talk will be as follows. So in the bulk of my talk, I'll try to explain the proof strategy of the proof of this theorem. Okay. And it will serve two purposes. On the one hand, of course, it'll be an expression of the proof of this theorem. But on the other hand, the deeper motivation is I wanted this would be a roadmap to a possible proof of this problem for the Yang-Mills equation. And then, if time permits, I'll report on the recent progress on this problem, which is obtained by collaboration with Daniel Tatar. Okay? Any questions? Okay. All Right. So let me describe to you the strategy of the proof of the global posedness and scattering theorem for the Maxwell-Klein-Gordon equation. And this is this builds upon the earlier strategy due to Sturbenz and Tataru, which was carried out in the case of the wave map equation. And so for concreteness, I'll focus on just the case of global posedness. Okay, I'll try to tell you how global posedness can be proved. So the whole argument is of course, contradiction argument. Okay, so we'll assume that global posedness fails, or in other words, finite time blow-up occur. And then we'll try to derive a contradiction. And as is well known, by the combination of the small data result and finite speed of propagation, you can immediately say that if you have a finite time blow-up, then it must happen by energy concentration at finitely many points. Okay, so what I mean is the following. So there will be some time before infinity where your solution breaks down, so you have finite time blow-up. You can identify a point on the final slice, such that if you look at the domain of influence of the point to the past, so it will be a light cone emanating from this point, and you measure so let's call the cross section of the intersection of the constant t slice and this cone as t. The energy measured on this st does not go to 0 as t approaches the final time. Okay, and of course you should contrast it with the case when this point is a part of the regular space-time, in which case by continuity this would of course go to 0. Okay, but then it turns out that you can say much more, and this goes in line with actually the picture that Piotr described yesterday, which is that you can say that blow-up, this concentration energy happens in a particular form. So what we prove is that you can extract a bubble from this finite blow-up with a particular profile. Okay? So what I mean by this is the following. So the claim is that you can find a sequence of times and space coordinates and scales lambda n. Okay, such that what you should have in mind is somehow there are these space-time coordinates which approach this tip of the light cone. So Tn approaches T plus these Xn remain in the in the cone, and there's sequence of scales which actually go to 0 faster than the radius of the cone. So it's little o of this, such that if you blow up this picture and make this scale lambda 1 to be unit, okay, so which means that we use the scaling to think about the following rescaled objects. So we rescale everything by lambda n centered at Tn and Xn. Then the sequence converge to something, to another solution to the Maxwell-Klein-Gordon equation in a strong local H1 sense. So to be more precise, on a sort of unit time interval, okay, where this object solves the Maxwell-Klein-Gordon equation. And what's more, it is a stationary solution to the Maxwell-Klein-Gordon equation. And in fact, I can even give you in which direction it is stationary. Okay, so by passing to some subsequence, you can assume without loss of generality that these points asymptote to some time-like curve. Okay, which I'll denote like this, and the generator I'll denote as y. Okay, and the solution turns out to be stationary with respect to that y variable. Okay, direction.
Why does it have to be time-like, not null, for example?
Well, short answer is because nothing with mass can travel at the speed of light,
Okay,
because of finite energy. Yeah. But this is an important point. Actually, it'll actually come up. So yeah. And by stationarity, I just mean the following. So the contraction of y with f formed by b is 0, and the covariant derivative of phi with respect to the y variable is 0. Okay. And then you say the following. Okay, well, we can always apply a Lorentz transform to y to make it a dt, right? And then the claim is this. The second claim, this is one claim. The second claim is that there does not exist any time-independent, or actually stationary, non-trivial finite energy solution to the Maxwell-Klein-Gordon equation. Okay, and this is very simple. You apply I can even give you a proof. You apply the Lorentz transform to make it dt. Then you realize these will obey the following equation. Okay, where it looks formally like the Maxwell-Klein-Gordon equation, but this is an equation on R4. And you just realize that you can multiply this equation by psi, integrate parts. This tells you that covariant derivative of psi is equal to 0. If you can multiply by parts. And this tells you that the equations decouple, and therefore f must be trivial. So you can take b to be 0, and then psi also has to be 0. And of course, the reason why you can do this integration by parts is because you have finite energy assumption. So it all boils down to showing this bubble extraction claim. Actually, I saved this board for this purpose. So, and of fundamental importance to this bubble extraction is a very beautiful monotonicity formula for the Maxwell-Klein-Gordon equation, which I'll now try to explain. So the key monotonicity formula which is responsible for this is something like this. Okay, so but I need to first fix some notations. Okay, so let me, for convenience, translate the singularity to the origin of my space-time. Okay, and moreover, let me flip the time direction so that I look at something that blows up to the past. Okay, I just want to work with sort of the this half space. And let me also assume, for simplicity, that I've cut off everything that happens outside this region, so that essentially the energy outside is very small. Okay, so that we only concentrate on what happens here. Okay, this can be done by some gluing of initial excision and gluing of the initial data. And in order to state the monotonicity formula, let me set up some notation. Okay, so let me introduce the vector field, which I call x, which is the normalized scaling vector field. Okay, so this is the scaling vector field, but then multiplied by a factor. so that its Minkowski norm is always equal to -1. Okay, so this rho is square root of p squared minus x squared. And if you plot this vector field here, it will just be something like this, right? So it'll always point in the scaling direction, right? But then you will see some degeneration as you approach the boundary of the light cone, because there this vector field becomes null. Okay. Let me also introduce some null variables, u, which is, according to my convention, t minus epsilon of x, and v, which is t plus epsilon of x. Okay. So in particular, it's chosen so that this boundary of the light cone is the u equals to 0 hypersurface. Okay. And with this, I'm ready to tell you the key monotonicity formula for bubble extraction. This is actually, okay, so let me just first state it. So let's take two time slices, which are called ST1 and ST2. Okay, so the monotonicity formula is something like this. So morally, the following monotonicity formula holds. So there exists some weighted non-negative energy quantity P, such that its integral on this slice bounds from below the integral of the same density on this slice, on the other slice, closer to the singularity. And in fact, the difference is given by a space-time integral of certain quantity density, which are called Q, which is also non-negative, up to some error, which goes to 0 as you approach the singular time. Okay. And here, this density of the space-time integral is given as follows: is 1 over rho times the interior the contraction of this x vector field to the Maxwell field squared, plus this self-similar derivative of phi squared. And this P takes the following form. P is some weighted energy quantity where up to constant vectors I'll probably mess up. It's this weight times the R inverse dV R phi squared plus the reverse weight times the U, the same quantity, R inverse du R phi squared plus these weights times the angular derivative plus a Hardy wave term. Okay, and furthermore, okay, and actually, in fact, there is also a contribution of some terms which involve A, which is non-negative. So I'll not talk about this. Okay. Okay. So a few remarks before. Okay. So I don't have much time.
It's not a strict monotonicity formula.
Right. So yes. So that was the first remark I'm going to say. So of course you might be puzzled how. Okay. It's curious that you see a monotonicity formula in a reversible, time reversible equation, wave equation, right? And of course the magic lies in this error term. Okay, which is actually the contribution of the flux. And in fact, the reason why you have this decay, so that you have this sort of formula modulo this error, is that you a priori have decay of flux, right? And decay of flux is just comes from the fact that the flux density energy flux density is non-negative. So you have finite integral. So if you take small, then it's going to go to 0. So let me just say that this error is due to flux decay, energy flux decay, which is a nice feature about this equation. And second, let me also say that I lied a little bit.
It actually goes to 0. Yeah, okay, sure.
Yeah. Okay, so I should also say that, let me not write it out because we don't have much time. I should say that this formula is actually only morally true because the way I wrote it, the weight you see actually goes to infinity at the boundary. Okay, so you need some regularization procedure, but let me stick with the prettier lie rather than the messier truth. Okay, you hope you believe me that that's a technical thing that can be worked out. Okay, but very nice. So what you get out of it, first of all, is the following: that you have, in fact, by independent means, you can prove that this integral, these integrals, is bounded from above by some absolute constant times the energy. Okay, so this is something that's always bounded, at least as you approach the singularity. And what this tells you is that this space-time integral is finite. Let me write it out. And this signifies the following. So look, there is a weight here, which goes to 0 basically linearly as you approach the tip. Right? So this signifies that the fact that this integral is finite tells you that there is some logarithmic decay of this integrand as you go to 0. Right? Otherwise, this cannot be finite. So this is actually the key crucial ingredient for the bubble extraction, as I'll try to explain now. So what this tells you is that morally, the derivative, this sort of time-like, derivative decays in some integrated sense as you approach the tip, right? So you want to make use of that. You want to say that you can extract a solution, extract a limit of a solution, sequence of solutions, and say that that must be stationary like that due to the decay of the integrated decay which comes from this, right? But then you have to divide into two cases. But then what you also realize is that there is degeneracy as you of this vector field as you go to the boundary of the cone, right? So this is only effective in a fixed, time-like cone, not in the whole cone. So you have to divide into cases. One, when there's when there exists a fixed time-like cone, which I call C tilde, such that some non-trivial amount of energy remains in the time-like cone. Okay. So this would be our case 1. And you also have to think of the case when this doesn't happen. And by time-like cone, I just mean a cone with opening which is strictly smaller than this null cone.
You've drawn it inside ST, but it's not the case because of your intersection?
Sorry? So right. So I'm only concerning energy in this region. So what this is trying to say is that this is the case when there's some energy remaining in a fixed time-like cone. Okay, and this is the case when the energy exits all fixed time-like cones. And let me just say that so what happens is that in the case of 1, the decay of such a time-like vector field is effective, okay? And this allows you to find the desired sequence of space-time and scales, which should give you the bubble extraction. You see, this explains why you have this particular direction of stationarity, right? Because this is nothing. So you imagine that you found these sequences, right? And imagine that you can do it in such a way that the same integrand decays, okay, in these boxes, and then you realize that that x vector field along asymptotically becomes this y vector field, right? The direction unit vector, time-like vector in the direction of this asymptotic time-like ray that these approach. But then, so is this okay?
So the smaller cone is at a given distance from the other one, right? So
Right.
it's
But then,
make sure that you actually get something time-like.
Right. But then the point is, in fact, you can actually extract such a sequence. I can't go. I don't want to go into details, but you can extract such a sequence if this holds for any fixed any fixed time-like cone. So the case where you cannot use that monotonicity formula is exactly when you cannot find such a cone. So in other words, the energy exits every time-like cone as you go toward the singularity. And in fact, this is precisely the case where you have to think about. This is precisely the case when everything sort of is traveling at the speed of light, right? And this is the case where you a priori would think that there cannot be any nonlinear bubbles, right? Because if there were any bubbles, then because of finite energy assumption, you cannot travel at the speed of light. And in fact, what you can do is you can now look at this statement that this weighted quantity is always bounded, and realize that it has a very good weight on certain components of the field phi, right? So in particular, the dv derivative of phi decays and the angular derivative of phi decays. And this tells you that, in fact, there cannot be any nonlinear bubbles and more quantitatively, you can say the following. In fact, one way to quantify this would be the following. So one way to find a concentration, a point-wide concentration, would be to look at phi and test this, integrate this on some ball of radius lambda, okay? But then weight it so that it's a dimensionless quantity. So you want to take something like, I think, this, okay? And say that this is very small. Well, this is a wave equation, so I need to take a time derivative as well. So I also take something like this. And the heuristics that I told you basically translates to the statement that such a quantity uniformly for all lambda and all x goes to 0 as you approach the singular time, okay? And of course, what's happening is that outside we cut off anything that's happening. Inside, there's no energy in any time-like cone, and and where the energy lives, there is no nonlinear bubbles. You have smallness of dv derivative and the angular derivatives, which give you this. And the key the wave regularity theorem that we prove precisely enters at this point. So the result is that if this is small enough, then we can continue the solution past 0. So there's a contradiction. If this holds, so this is a contradiction. And this is the summary of the proof. So I think I ran out of time, so I can't say anything about Yang-Mills. So I'll just stop here. Thank you.
Thank you.
Cedric.
So, if I understand correctly, this monotonicity formula, which is not a monotonicity formula,
Yeah, well, yeah, it's hidden. Yeah, yeah.
it doesn't give you any a priori estimate on any solution. You have to take different cases and use it differently in different cases. Is that correct? Or
Yeah, I mean, well, it's a
because by itself it doesn't tell you much, right?
yeah, it's a very weak decay statement that it tells you, right? All it tells you is that there's this integral quantity is bounded, right? So this tells you that sort of the integrand actually decays in some logarithmic sense.
But even that I don't understand because you don't have information about ST2, right? The right hand.
Oh no, so what you can do is, because you know that this is, so I was saying that by separate means you can show that this is always bounded. And this means that you can take T2 to 0, right? It's uniformly bounded. So that will tell you that this spacetime integral is bounded.
But the spacetime integral comes out in the Q, right? And it's part of the Q.
Yeah, but it's on the left hand side.
Right, but okay, well, I have to ask you afterwards. I still don't understand.
This is uniformly bounded for any T2. That's something that you can prove. Okay. So you can take just T2. Yeah.
Fine.
Two questions, but short. This last theorem, you use Ricards?
Oh, that's a so of course, but we also have to use sort of bilinear estimates and so on. So
Why is it complicated?
why is it complicated?
Because for the wave we have the same thing with.
Yeah, that's a very good point. So in fact,
because we use Sobolev and we mix Sobolev and Ricards. So this is more delicate.
yeah. So yeah. Right, exactly. So you see, the phi equation, if you expand, has a term which is a times derivative of phi.
Okay.
And okay, you're right. So this actually statement is a complete triviality for the semi-linear, for the power type nonlinearity, because in there what you can say is that in the nonlinearity you can use Strickhart's to say that you have very good off-diagonal decay in if you decompose into little Pelé pieces, right? And the point is that this translates to smallness of some Besov norm. Yeah, and that's it. But then here you realize that because of the presence of the derivative and the wave equation only gains one derivative, there's no exponential decay between the low frequency part of this and the high frequency part of this.
Okay.
So this is actually the key difficulty that one has to face.
Okay.
Yeah.
And the second question, okay, this is, I guess, the natural extension of the formula I have with Zag for the critical wave equation.
Yeah.
Okay. So you don't go back, as in the proof I have with Carlos, to 0 outside. When you have a real monotonicity formula, then you are done in some sense. You don't have to worry about the
Right. But then that's when you construct a minimal counterexample. Right. So I mean, I guess the point is this is more a more direct approach. So we are now assuming that we have a minimal counterexample. We're assuming that give us any counterexample.
But then, okay, so the thing I don't understand is you use approximation of cone inside and not outside.
Mm-hmm.
Outside is not easier?
Outside outside is actually, because of finite propagating and flux decay, outside is very easy. So
Yes.
Yeah.
You control all these terms. So it's okay. Okay.
Yeah.
Anyway, I can discuss with you. With
Well, we continue in 15 minutes. Thank you.